This specimen is low-density polyethylene. The relevant data has been entered into the software and the rate of extension is 65 millimeters per minute. Testing now. Currently there are quite low forces involved in this test, around just under 400 newtons. Significant stress elongation can be observed. Some dimples appear here, stress necking, and fracture. Having removed the two halves from the grips, the colouring on the fractured faces is much lighter than the main material. Therefore, low-density polyethylene stress necks and stress whitens. From the plot of force against displacement for low-density polyethylene, the maximum load was not hugely over 350 newtons. Tap on calculating results. It shows 377.72 newtons for maximum force. It's F max. This specimen is high-density polyethylene. The relevant data has been entered into the software and the rate of extension is 65 millimeters per minute. Beginning the test now. The low-density polyethylene, the yellow specimen, its change in shape and colour occurred just before fracture. For high-density polyethylene, some stress necking is observed here. With this polymer, this indicates that the fracture is most likely to occur here. The area is lightening in colour. Therefore, for high-density polyethylene, it will stress neck and stress whiten before failure. Consequently, high-density polyethylene is giving plenty of warning that it is going to fail. There was notable lightening just before failure. Looking at the two plots where green is low-density polyethylene and the high-density polyethylene is in blue, high-density polyethylene is a much more organized structure. Up to 80% of its structure is crystalline, meaning there are a lot more cross-linked bonds between the long parallel molecular chains. The low-density polyethylene has up to only 40% of crystallinity. Consequently, on the graph where there is a peak in load, the polymer chains are resisting the forces being applied to it within those high crystalline cross-linked areas. Once those cross-links are broken, here, the high-density polyethylene behaves very similar to the low-density polyethylene. About the same amount of force is required between the two. This is a low-density polyethylene just below 400 newtons, and the high-density polyethylene requiring less than 500 of newtons of force to maintain the rate of extension. In both cases, the rate of extension was 65 millimeters per minute, so once those high crystalline crosslinks are broken, high-density polyethylene basically behaves the same as low-density polyethylene. These are some pre-tested specimens of high-density polyethylene and low-density polyethylene. Both sets of thermoplastics have been tested at the same rates of extension, between 25 mm per minute to 100 mm per minute, 25 to 100. Between the two, the low-density polyethylene, regardless of the rate of extension, the polyethylene results in a similar ductility after fracture. However, in the case of high-density polyethylene, this is very rate dependent on its properties of ductility and how it behaves. At the three lowest rates of extension, 25 mm, 50 mm, and 55 mm per minute, the high-density polyethylene did not fracture. In fact, it reached the top of the Instron universal testing machine and it remained intact. If the machine was taller, it would eventually fracture, even at these low rates of extension.